A single telescope has just revealed something impossible. We once believed the universe spanned 14 billion light-years, but a staggering new discovery shows it actually stretches across a distance of 93 billion light-years. What if our entire understanding of creation was only a tiny fraction of the actual truth? Are you ready to see what is truly hidden in the deepest reaches of space? The James Webb Space Telescope recently pointed its lens at a patch of sky that appeared completely empty. In that deep darkness, it found 800,000 galaxies that we never knew existed. These massive structures were born when the cosmos was only 300 million years old. We are seeing black holes that are billions of times more massive than science thought possible for that era. We are witnessing structures tens of millions of light years long that theoretically should not have had enough time to grow. Everything we thought we knew about the history and the size of our universe was wrong. We are beginning a journey to the very edge of reality, where the old laws of physics no longer seem to apply. A beam of light began its journey only 280 million years after the Big Bang. For more than 13 billion years, this light traveled through the ever-expanding void of space until it was finally captured by the golden mirrors of the James Webb Space Telescope. This discovery, officially confirmed in the year 2025, is known as Mome Z14. It has forced us to look back at a time when the cosmos was still raw and incredibly young. To understand how unbelievable this find is, we must look at the timeline. Our universe is 13.8 billion years old today. Mome Z14 already existed when only 2% of that time had passed. If the entire history of the universe were compressed into a single calendar year, this galaxy would have appeared as early as January 7th. We are looking directly into the childhood of the cosmos. We can only see this wonder because of the telescope's ability to hunt for what scientists call redshift. As light travels across billions of light years, the universe itself expands. This expansion stretches the light waves, pulling them away from visible colors and into the infrared spectrum. The farther away an object is, the more its light is stretched. Mome Z14 has a redshift value of 14.44, a number that represents an extreme, mind-bending distance. However, the scientific community is most shocked because Mome Z14 is not a small, faint smudge. Instead, the galaxy shines brilliantly, producing new stars at a staggering rate. Researchers even detected nitrogen within it, suggesting that star formation back then functioned similarly to how it does in our own Milky Way today. According to our old models, this should be impossible. We used to believe that galaxies grew slowly over hundreds of millions of years, but Mome Z14 proves that the universe in its youth was much faster and more powerful than we ever imagined. The discovery of Mome Z14 is likely just the beginning of our journey into the unknown. By the year 2027, the Nancy Grace Roman Space Telescope will be launched into service. Unlike previous instruments that focused on small, specific patches of the sky, this new telescope is designed to scan vast areas of the heavens all at once. It will almost certainly lead us even deeper into the past, taking us nearly to the moment of the Big Bang itself. Yet with every new discovery, we face the same haunting riddle. We keep finding objects that theoretically should not exist yet. We are seeing structures that form too rapidly, shine too brightly, and appeared far too early in the cosmic timeline. The universe had less than 300 million years to bring Mome Z14 into existence. While that sounds like an eternity to us, on a cosmic scale, it is nothing more than a brief blink of an eye. To grasp how fast this process really was, consider a comparison. Our Earth has existed for approximately 4.5 billion years, and the era of the dinosaurs lasted 165 million years. Mome Z14 pulled itself together in a shorter span of time than that prehistoric epoch. In that narrow window, stars ignited, gases collapsed, and massive galactic structures emerged from the darkness of the young cosmos. Our current understanding of how the universe began is starting to collapse. And this is only the start of the mystery. The James Webb Space Telescope does not see the world the way we do. It cannot perceive visible light. Instead, it captures infrared radiation, which is entirely invisible to the human eye. This specific technological choice is exactly what makes the telescope so powerful when it comes to exploring the very beginnings of our universe. To understand the full impact of this, one thing must be made clear whenever we look up at the stars. We are always looking directly into the past. The light from the star closest to us takes over 4 years to reach our eyes. This means we see that star today exactly as it existed 4 years ago. James Webb takes this principle to the absolute extreme. It stares at objects whose light has been traveling through the emptiness of space for over 13 billion years. The telescope functions as a time machine because infrared light is the key to history. Since the universe expands every second, everything within it is stretched, including light waves. Light that once began as ultraviolet radiation is pulled apart over billions of light years until it lands completely in the infrared range. Earlier telescopes like Hubble could never find galaxies like Mome Z because their light was beyond what they could technically detect. To sense these tiny ancient signals at all, James Webb must stay at a location called Lagrange Point 2, roughly 930,000 miles away from Earth. There, it remains an eternal shadow because its sensors must be kept extremely cold. Even the slightest heat would drown out the faint glow of distant galaxies. The instruments operate at about -370 degrees Fahrenheit, which is colder than the surface of Pluto. Only in this absolute icy cold can the time machine perform its work. To capture the invisible glow of the first galaxies, humanity required far more than just a simple camera. We needed a technological masterpiece operating at the very edge of what is physically possible. The heart of this effort is the primary mirror of the James Webb Telescope, a massive structure 21 feet in diameter. It is composed of 18 individual hexagonal segments, beautifully arranged like a golden honeycomb. Every segment is coated with a microscopic layer of applied gold, a material chosen because it reflects infrared light better than any other element we know. This specialized coating allows the telescope to pick up light particles 100 times weaker than anything the Hubble telescope could ever detect. Hidden behind these mirrors are tiny motors that adjust their curve and position with a precision that defies our imagination. This allows the entire mirror to focus perfectly, gathering the faintest signals from billions of light years away. But how do we find these tiny relics in the infinite blackness of space? The answer lies in the incredible patience of astronomy. Scientists program the telescope to stare at one specific patch of sky for hours or even days. During this time, photons sent out by distant galaxies eons ago trickle into the sensors one by one. It is a slow, meditative process where the image is built, layer by layer. Galaxies that were once invisible suddenly emerge from the darkness through this persistence. Once a breathtaking image has finally emerged from the deep silence of the void, the James Webb Space Telescope prepares to use its most formidable instrument. While the cameras provide us with a visual map of the heavens, it is the spectrograph that allows us to truly understand the nature of what we are seeing. This instrument is widely considered the most powerful tool in the telescope's arsenal, acting as a bridge between mere observation and deep scientific discovery. The prism of the cosmos. The way this technology works is both simple and profound. The spectrograph takes the light collected by the massive golden mirrors and splits it into its individual wavelengths. This process is very similar to how a simple glass prism catches a beam of sunlight and spreads it out into a beautiful rainbow of colors. However, for the scientists operating James Webb, this rainbow is much more than a visual wonder. They call the result a spectrum, and it serves as the ultimate chemical fingerprint of a galaxy. Every single element in the universe, from the simplest gas to the heaviest metal, leaves a unique and unmistakable signature within this light. As the light travels across the vastness of space, the atoms it encounters absorb specific frequencies. When the spectrograph analyzes this light, those missing frequencies appear as dark lines or patterns. By reading these cosmic fingerprints, James Webb can tell us exactly what a galaxy is made of, even if that galaxy is so far away that we could never hope to visit it or see it clearly with our own eyes. Decoding ancient chemistry. Through this incredible precision, we can detect the very building blocks of the early cosmos. We can see the presence of hydrogen and helium, which were the primary ingredients of the universe shortly after the Big Bang. But even more excitingly, the spectrograph allows us to find heavier elements like oxygen and carbon. These are the essential elements that would eventually go on to form planets, rocks, and the very chemistry of life itself. Seeing these elements in a galaxy billions of light years away tells us that the universe was preparing the way for life much earlier than we ever suspected. The key to time and distance. Beyond identifying chemicals, the spectrograph provides the most critical piece of information in all of astronomy, the exact measurement of redshift. Redshift is the universal key that scientists use to determine the true distance and age of every object in the sky. By seeing how much the light waves have been stretched toward the red end of the spectrum, we can calculate precisely how long that light has been traveling and how fast the galaxy is moving away from us. This measurement is what allows us to say with certainty that we are looking at an object from the dawn of time, a sea of infinite worlds. When we look at the deep field photos created through this technology, we are not just looking at a pretty picture of the stars. We are looking at thousands of galaxies, captured in a single frame. Each one of those tiny glowing points is a world of its own, a vast system of stars, planets, and mysteries that we may never fully explore. Yet, even though they are out of our reach, we can still understand them. We see these galaxies as they were when the universe was just a child, in their ancient light. We are essentially reading the history of our own origins. It is a massive technical achievement that serves as a constant reminder of human potential. Even though we are small and confined to one tiny planet, we have built a machine capable of peering into the deepest secrets of time itself. Imagine for a moment a state of perfect and absolute void following the monumental event of the Big Bang. The universe did not immediately burst into the brilliant display of light we see today. Instead, it sank into a deep, silent darkness that lasted for hundreds of millions of years. In this era, which modern astronomers refer to as the Dark Ages, there were no burning suns, no glowing galaxies, and not a single flicker of light to pierce the heavy blackness. The entire cosmos was filled with a massive, cold soup of neutral hydrogen and helium gas, drifting undisturbed through the expanding emptiness. There was no structure, no heat, and no life. It was a universe of potential, waiting for a catalyst. Yet, within this apparent silence, an invisible and relentless force was working without pause. Gravity, the invisible architect over unimaginable periods of time. The gravity of the dark matter and the gas itself began to draw the universe together. Gas clouds started to collect in dense pockets, pulled by the unyielding hand of gravity. These pockets grew larger and heavier, drawing in more and more material from the surrounding void. As these gas clouds became more massive, the pressure at their centers began to rise to extreme levels. Temperatures climbed into staggering heights, reaching millions of degrees. Then, in a single sacred moment, the impossible happened. The pressure became so great that the nuclei of hydrogen atoms began to fuse together. The first spark ignited. Nuclear fusion had begun, and with a sudden, violent burst of energy, the eternal night was ended. This hallowed moment marks the beginning of the cosmic dawn, the epoch where the first light began to flood the universe. The giants of the dawn, the first stars, born in this morning of time, were fundamentally different from our own sun. Scientists call them population 3 stars because the early universe contained no heavy elements like carbon or oxygen. These stars formed from pure hydrogen and helium. These giants were likely 50 to several hundred times more massive than our sun. They burned incredibly hot, shining with a blinding blue light and emitting massive amounts of ultraviolet radiation. This intense light began to change the very nature of the universe. The ultraviolet radiation struck the surrounding neutral hydrogen atoms and stripped away their electrons, a process known to science as ionization. Around each of these first stars, a growing bubble of ionized plasma began to form. The end of the fog. At first, these islands of light were isolated, scattered far apart in the infinite darkness. However, as more and more stars ignited and the first small galaxies began to emerge, these bubbles grew and eventually started to overlap. Within just a few 100 million years, the universe transformed from a dark, neutral space into a brilliant, ionized plasma. This transition occurred in what is, by cosmic standards, a mere blink of an eye. By approximately 400 million years after the Big Bang, the majority of the cosmos had been reionized. It was a time of extreme upheaval that laid the foundation for everything we see today. Without these first gargantuan stars acting as cosmic alchemists, there would be no planets and no life. We are the witnesses to the echoes of this great awakening, seeing light that has traveled 13 billion years to tell us the story of the very first dawn, when the James Webb Space Telescope transmitted its first deep-field images back to Earth. Astronomers immediately noticed something peculiar, tiny, unassuming red specks scattered across the cosmic tapestry. At first glance, they appeared to be nothing more than ordinary, distant galaxies. However, as the spectroscopic data came in, it revealed a reality that is bordering on the supernatural. These objects, now famously known as the little red dots, seem to violate almost every established rule of galactic development that humanity has spent decades trying to perfect. The mystery of the red specks. These dots are incredibly small, far smaller than any typical galaxy from that same ancient era. Yet they glow with a power that is physically difficult to explain. This creates a massive paradox for researchers. There are only two ways an object so tiny can shine that brightly, and both options are equally shocking to the scientific community. The first possibility is that these galaxies are packed so tightly with stars that they should be constantly colliding with one another, a phenomenon we simply do not see in any modern galaxy. The second, and perhaps more terrifying possibility, is that at the heart of each of these tiny dots sits a supermassive black hole that is far too large for the galaxy it inhabits. A broken balance in the modern universe, such as in our own Milky Way. There is a clear and consistent balance. The central black hole usually accounts for only about 0.1% of the total mass of the stars in the galaxy. This represents a ratio of roughly 1 to 15,000. But in these ancient little red dots, this fundamental law is turned completely upside down. In these systems, the black hole can weigh as much as all the stars in the galaxy combined. It is as if the black hole was created first, and the galaxy itself was merely an afterthought of creation. A perfect example of this cosmic madness is a system named Canucks LRD Z86. This galaxy existed only 570 million years after the Big Bang. Deep inside it lies a black hole that is already millions of times heavier than our Sun. It is devouring matter at a speed that breaks every theoretical limit we have. Under normal circumstances, a black hole requires billions of years of consuming gas, dust, and stars to reach such a size. This object simply did not have that kind of time. Defying the laws of physics, even more unbelievable is the black hole known as Liddy 568. Data from both James Webb and the Chandra X-ray Observatory show that this monster is swallowing matter 40 times faster than the Eddington limit should allow. In physics, there is a theoretical speed limit for how fast a black hole can feed, because the radiation produced by the falling matter usually pushes other incoming material away. This monster, however, ignores the laws of physics entirely and grows at a murderous pace. The existence of these objects tells us that black holes in the early universe were born much faster and much hungrier than we ever imagined possible. They did not need eons to grow. They appeared early, aggressive, and ready to consume everything in their path. The youth of our universe was not a calm period of slow growth. It was wild, violent, and incredibly fast. Every new observation is forcing us to throw our old equations and simulations into the trash. We are learning that the universe was never patient. It was a place of impossible extremes from the very beginning. Imagine for a moment that you are standing under the vast canopy of a clear night sky. You reach down to the ground, pick up a single grain of sand, and hold it at arm's length toward the heavens. To your eyes, that tiny speck seems completely insignificant against the backdrop of the infinite void. However, the truth hidden within that microscopic area is enough to change your entire perception of reality. Within that space, covered by a mere grain of sand, there are nearly 800,000 galaxies. This staggering number is the result of the Cosmos Webb survey. To capture this image, the James Webb Space Telescope performed a feat of incredible endurance, staring at a single, seemingly empty patch of space for over 200 hours without interruption. The area investigated covers only 0.6 square degrees of the sky. To help you visualize the scale, the full moon covers about 0.2 square degrees. That means we are looking at a patch of the universe about 3 times the size of the full moon. In the grand scheme of the cosmos, this area is nothing more than a microscopic sliver of infinity. Yet, within this tiny sliver, James Webb has revealed more galaxies than most human beings can truly comprehend. We are looking at 800,000 galaxies, and every single one of them contains billions or even trillions of stars, because these galaxies are located at vastly different distances from us. This single observation acts as a massive timeline of cosmic history. In one frame, we see objects that are in our relatively close neighborhood right next to those whose light has been traveling for over 13 billion years to reach us. Using the near-infrared camera and the mid-infrared instrument, researchers were able to collect data that far exceeds any knowledge we had before. Scientists specifically chose this field of view because it is remarkably clear. There are very few stars from our own Milky Way or thick gas clouds to block our sight. It offers a perfectly free line of vision straight into the deepest reaches of the past. For years, the Hubble telescope studied the same region, but much of the reality remained hidden in the shadows. It took the power of James Webb to finally reveal those galaxies that were completely invisible to Hubble. The true revolution of this project lies in its incredible combination of width and depth. While many space images focus on a single, tiny point to find the faintest light, the Cosmos Webb survey covers a much larger area. The result is a comprehensive map that shows us exactly how galaxies are distributed through space. It is a map of massive galactic structures, clusters, and the giant empty voids that stretch across billions of light years. As we scan this map, we see galaxies at every possible stage of their evolution. We see elegant spiral galaxies with glowing, spinning arms, smooth and featureless elliptical galaxies, and irregular formations being torn apart by the gravity of their neighbors. We can even witness galaxies in the middle of violent collisions, their shapes being shredded in a massive cosmic dance. And everywhere we look, like glowing sparks in the dark, we find the mysterious little red dots from the very beginning of time. Perhaps the most shocking discovery from this survey was the sheer number of early galaxies. Our previous scientific models predicted that there should be very few bright galaxies in the first billion years after the Big Bang. However, the Cosmos Webb survey found 10 times more than anyone expected. This leads to a profound conclusion: galaxy formation was far more efficient and happened much faster than our theories ever suggested. Even massive galactic structures like groups and clusters, which should have taken much longer to form under the laws of gravity, are already clearly visible in this early stage of the universe. In the infinite silence of the deep cosmos, there are phenomena that challenge our very understanding of stability and gravity. Imagine a supermassive black hole, a monster weighing 10 million times as much as our sun, racing through the void at a staggering speed of 2 million miles per hour. This is not an object orbiting a quiet center, nor is it a stationary anchor of a galaxy. Instead, it is on an eternal flight, a cosmic fugitive cast out into the emptiness between worlds. As this giant moves, it leaves behind a breathtaking and haunting mark on the universe, a cosmic scar of light that stretches for 200,000 light-years. This is a trail of newborn stars, ignited by the sheer force of the black hole's passage. It is a rare and beautiful sight, a destroyer of worlds acting as a creator, leaving a path of brilliant fire in its wake. The physics of the Great Escape. How does an object so massive get thrown out of its home to launch a supermassive black hole into the void requires a force beyond our everyday imagination. This particular runaway was catapulted from its host galaxy with a power that sent it screaming through space at 3,000 times the speed of sound. This discovery, which was officially confirmed by the James Webb Space Telescope in the year 2025, represents the first verified runaway supermassive black hole in human history. The event took place in a distant system known as the Cosmic Owl, a chaotic region where multiple galaxies are currently merging together. Normally, when galaxies collide, their central black holes slowly sink toward a new shared center. However, sometimes the dance of gravity becomes unstable. If a third black hole enters the fray, the resulting gravitational interaction can act like a giant cosmic slingshot, firing one of the monsters into the darkness at impossible speeds. James Webb was able to track this fugitive by detecting a bug or bow shock wave in front of it. As the black hole plows through intergalactic gas, it compresses the material so violently that it triggers the birth of stars along its flight path. It is a spectacle of pure physics, the compression of cold gas into burning suns, all because the invisible giant is passing through. A universe of violent collisions. This runaway giant is not the only violent event James Webb has witnessed in the depths of time. In another system named ZS7, the telescope captured two more giants locked in a deadly embrace. This system existed only 740 million years after the Big Bang, a time when the universe was still in its earliest youth. Here, two supermassive black holes, each millions of times heavier than our Sun, are spiraling toward each other. When they eventually collide and merge, the impact will be so powerful that it will shake the very fabric of space and time. James Webb identified this merger by analyzing the light spectrum, which revealed two distinct sources of intense energy squeezed into a very small area. This is the earliest and most distant merger of black holes ever detected. It provides a crucial answer to one of the biggest mysteries in astronomy. How did black holes get so big, so fast? Instead of just slowly eating gas over billions of years, these monsters can double their mass in an instant through a violent union. While we cannot yet directly measure the gravitational waves from ZS7 because they have traveled 13 billion light-years and become too weak, the future of our exploration is bright. Upcoming observatories like LISA, scheduled to launch in the 2030s, will be designed to listen for these exact cosmic echoes. For now, James Webb has given us a preview of a young universe that was far more crowded, active, and violent than we ever dreamed. In the unimaginable depth of time, there exists a galaxy known as JWST 140. This distant world was observed at a point when the universe was merely 290 million years old. What the James Webb Space Telescope discovered there challenges every boundary of our imagination. This galaxy is birthing new stars at an absurd speed, 100 times faster than any scientific model had predicted for its age. To truly understand the intensity of this galactic furnace, we must look at how a star is born. Massive clouds of hydrogen must collapse under their own gravity until they reach temperatures of 10 million degrees, at which point nuclear fusion ignites. In our modern Milky Way, this process is relatively slow, producing about 3 new stars every year. But JWST 140 is a cosmic forge, a place where thousands of stars are coming into existence simultaneously. Scientists are currently struggling to explain how such a small, young galaxy could be so productive. One leading theory suggests that cold streams of gas from the surrounding space poured into the galaxy like rivers into a lake, providing a constant supply of fresh fuel. Another possibility is that a violent collision with another galaxy compressed the gas so intensely that it triggered star births everywhere at once. There is even the chance that this galaxy was home to hypothetical supermassive stars, hundreds of times heavier than our Sun, which shone with the brilliance of entire star clusters. Every discovery of this nature forces us to rewrite our cosmic timelines, revealing the early universe as a far more violent and productive place than we ever dared to believe. The mystery of the growing universe. While we marvel at the birth of these first galaxies, we are also standing before an even greater mystery. How fast is the universe actually expanding? Since the 1920s, we have known that our cosmos is growing. But today, 2 different methods of measurement are providing 2 completely different answers. Astronomers refer to this baffling dilemma as the Hubble tension. When scientists analyze the afterglow of the Big Bang, the very oldest light in existence, they calculate an expansion rate of approximately 67 kilometers per second per megaparsec. However, when they look at nearby stars and supernovae directly, they arrive at a value of approximately 73. This difference of 6 points is not a simple calculation error. The James Webb Space Telescope has carefully double-checked the measurements made by the Hubble telescope and confirmed that these numbers are accurate. This confirmation means that something fundamental is missing from our understanding of the universe. Perhaps the mysterious dark energy that drives the expansion of space behaves differently than we thought, changing its strength throughout history. Or perhaps there is an entirely unknown form of energy or matter that we have yet to discover. The Hubble tension is a visible crack in the foundation of our cosmic models. It serves as a powerful reminder that despite our incredible technology, we are still only at the very beginning of understanding the true nature of creation. In the deepest, most distant reaches of observable space, the James Webb Space Telescope has encountered a galaxy known as LAP-1b. The light captured from this ancient place was unlike anything astronomers had seen before. When the instruments analyzed its spectrum, they found a startling absence. There was almost no oxygen and no carbon to be found. Instead, this galaxy was composed almost entirely of hydrogen and helium. This discovery represents the long-sought signature of the very first stars to ever ignite in our universe, the legendary population 3 stars. In the language of astronomy, any element heavier than helium is considered a metal, while a modern sun like our own is rich in these metals. The first generation of stars was born from the pure, raw matter that existed immediately after the Big Bang. These gargantuan stars were the true cosmic alchemists. They burned with a fierce, hot blue light, yet their lives were tragically short, lasting only a few million years before they vanished in spectacular supernova explosions. It was only through their violent deaths that the universe was transformed. As these stars exploded, they scattered the very first heavy elements across the void, creating the essential building blocks for everything we know today. Every star we see in the night sky and every atom within our own bodies contains metals that were once forged in the hearts of these ancient giants. The iron that carries oxygen through your blood and the carbon that forms the ladder of your DNA are the direct legacy of this first generation of stars. The revelations provided by the James Webb Space Telescope show us a universe that is far more dynamic and complex than any of our previous models predicted. We now know that galaxies formed much faster. Black holes grew with terrifying speed, and massive cosmic structures appeared much earlier than we ever thought possible. But what does this mean for us? Sitting on a small planet orbiting an average star in a common galaxy, it means, above all else, that we are inextricably linked to the cosmos. We are not merely observers of the universe. We are made of its very fabric. We are, quite literally, made of stardust. As we look at these images of the deep past, they reveal our own staggering insignificance. In a universe containing 2 trillion galaxies, each home to billions of worlds, a single human life might seem like nothing more than a whisper in a storm. Yet, there is something unique and profound about our species. We have become the eyes of the universe. We are the part of cosmic matter that has organized itself in such a way that it can now study the matter from which it came. We have reached across billions of light years of empty space to decode the secrets of our own origins. Despite the flaws in our scientific models and the deep mysteries of dark energy and the expansion of space, our curiosity remains our greatest strength. Every answer we find only brings new and more beautiful questions, moving us one step closer to the ultimate truth. The universe is unimaginably vast and ancient, yet we have dared to look beyond the boundaries of time to witness the very dawn of creation. We are small, and our time here is short, but in our ability to wonder, to learn, and to discover, we become one with the infinity that surrounds us.